Alright, so for problem number 7, we want to prove the remaining parts of Theorem 2.2.1, as some of these have already been proved in the textbook. So let's begin with item A, and we want to show that set A is a subset of A union B. So we're going to say let X belong to A, and whenever we want to show that something's a subset, we want to produce some element that is here and show that it shows up in there, right? So if X belongs to A, then X belongs to A or X belongs to B. Because if it does belong to A, then the statement will always be true, right? Because an or statement is true whenever one of them is true. It doesn't have to be both. So X belongs to A union B, because this is the definition, right? Belongs to the union if it belongs to A or B. Thus, A is a subset of A union B. So this one's pretty straightforward. Now let's do item C. And this one we're going to do by contradiction. We're going to first assume that there is some element here and then show that that leads to a contradiction, and therefore there's no element there, so it must be the empty set. So we're going to say let X belong to A intersection with the empty set. Then by definition, then X belongs to A and X belongs to the empty set, because this is just the definition of intersection. But X cannot belong to the empty set, as the empty set has no elements. Which is a contradiction. So we've shown that a contradiction has taken place, which means that our initial assumption, this guy here, that was wrong. So the conclusion is, so X does not belong to A intersection of the empty set. So we've shown, because we've taken an arbitrary member of that set, and we said that, hey, that arbitrary member can't be there. So this implies that there are no members in that set. So there is no element in A intersection with the empty set, so it must be the empty set. And that is it for our conclusion. We've just shown this by contradiction. Okay, now let's do item D. So item D, we want to show that A union with the empty set is equal to A. And this we are going to do A biconditional. So, and the reason that we're doing A biconditional is because to prove that something is equal, we have to show a double inclusion. We have to show that the left-hand side implies the right-hand side and vice versa, right? So we're going to say we have that X belongs to A union the empty set, right? If and only if X belongs to A, or X belongs to the empty set, if and only if X belongs to A. So this is very, very straightforward, right? We from here we can see that we can reason in this direction. If X belongs to A, then it belongs to A or the empty set, then it belongs to the union, right? And we can reason backwards. We can reason that if X belongs to the union of A with the empty set, then it belongs to A or the empty set, then it belongs to A. So we have shown here a double inclusion, and that is sufficient. So the next one that we want to do is we want to do item E. And once more, we're just going to do this using A biconditional. So we're going to say we have that X belongs to A intersection A if and only if X belongs to A and x belongs to A, because this is just the definition of intersection, if and only if x belongs to A. And so, oh, I forgot to put earlier in the example, I should have done, sorry, let me move this down. I should have done here, therefore, A union the empty set is equal to A. And here, therefore, A is equal to A intersection with A. So that is it. Whenever we have a biconditional, we want to make sure that we can reason going in this direction, right? And then also going backwards in between each line, which we can do here quite easily. So that is it for item E. The next item that we have to do is item G. So once more, we're probably going to do a biconditional here. Let me just erase this. Okay, so for item G, we're going to do, we have that x belongs to A union B, and that's going to be if and only if x belongs, oops, I should do x belongs to A or x belongs to B, if and only if x belongs to B or x belongs to A, if and only if x belongs to B union A. So therefore, A union B is equal to B union A. So we've just shown here through a biconditional that it works. It's pretty straightforward once more. And all we did here was we just switched the order, because if this is true, then this is also true, right? So all we did was switch the order, and that directly leads us to the definition of x belonging to B union A. So the next that we want to do is going to be item, I believe it's item I, yes. So we're going to say here. So for item I, once more we're going to use a biconditional, so we have that x belongs to A minus the empty set, if and only if. So the definition for one set minus another is if x belongs to A and x does not belong to the second one, right? So if and only if x belongs to A and x does not belong to the empty set, and this is always true because x will never belong to the empty set. So, and that's if and only if x belongs to A. So, therefore, A minus the empty set is going to be equal to the, it's going to be equal to A. So, pretty straightforward, right? All we're doing here, we can see that if we can also reason backwards, if x belongs to A, then it belongs to A and it does not belong to the empty set, then it belongs to A minus the empty set. Next one that we have to do, I believe, is item J. Now, item J, we're going to follow the same structure, but it's going to feel a little bit differently. So item J here. So we're going to say so I'm going to begin arguing backwards. So because previously I had began with the left and I showed that it leads in a biconditional we could arrive to the right, and now I'm going to begin backwards, right? I'm going to say we have that x belongs to the empty set. Now this is already false because x cannot belong to the empty set, right? And we just have to remember one thing about the biconditional, the if and only if. If I say P, if and only if Q, this statement is true under two circumstances. If both P and Q are true, or if both P and Q are false. So because this is a false statement, I need to argue that everything that comes after it is false, right? So because this is a biconditional, it's kind of like what we were doing before, where we were arguing with the biconditionals where every single statement was true, but now we're going to make that every single statement is false. And in this way, the biconditional becomes true. So we have that x belongs to the empty set if and only if x belongs to the empty set, and what do we want? And x does not belong to A. Because remember, we're trying to get here, where x belongs to the empty set and x does not belong to A. So if and only if x belongs to the empty set minus A. And so therefore, the empty set is equal to the empty set minus A. So once more, because this first line is false, then every single line that follows after it has to be false, right? Because if and only if x belongs to the empty set and x does not belong to A, that's clearly false. So x belonging to the empty set minus A also has to be false, right? And then if everything's false, then this biconditional becomes true automatically. Okay, so that was it for item J. It was a little bit strange, but we got through it. Now we have item K. So for item K, we want to prove this here, and maybe I'm going to do this by the biconditional. That also works. So we're going to say we have that x belongs to A union B union C. And what I want to do here is I want to expand it so that we get here, right? And the way that I'm going to do this is I'm going to say, oh wait, let me just improve my handwriting. Okay, well, if x belongs to A union B union C, if and only if x belongs to A or x belongs to the second one, right? Because first we're applying the definition of this first union. So if and only if x belongs to A or x belongs to B union C, if and only if x belongs to A or, and now we're going to unravel this one, if x belongs to B union C, it either means that x belongs to B or x belongs to C, or x belongs to B or x belongs to C. And now what we're going to do is just put a parenthesis here, because now we're going to join these with a union, right? If and only if x belongs to A union B or x belongs to C. So all we did here was we fully expanded into 3 or statements, and then instead of doing like x belongs to A or x belongs to, our parenthesis x belongs to B or C, then we're just going to put the parenthesis elsewhere, and that is totally fine. And so once we're here, we're going to say if and only if x belongs to, now we're going to join these two here. So A union B or x belongs to C means A union B union C. So that is it for item K. Now we have to do item L, which is pretty similar, but except we're going to do now with an intersection. So let me erase all of this. Okay, so for item L, so that's going to be item L, and we want to begin here. So we have that x belongs to A intersection of B and C. Now our objective is the same because we have 2 intersections, so our objective is to expand this to 3 and statements, and then just put a parenthesis in a different place. So if and only if x belongs to A and x belongs to B intersection C. So we've unraveled this first intersection. If and only if x belongs to A, and now we're going to unravel this intersection here. So we're going to say and x belongs to B, and oops, that was terrible handwriting, and X belongs to C. And all we're going to do here is we are going to, because previously it's like the parentheses were here. Actually, maybe I'm gonna leave this here and I'm gonna copy it into a new line. I think that will be a more intuitive approach. So let me just copy, and I'm gonna paste this here. And the only thing that I'm gonna do is I'm gonna move the parenthesis. So I'm gonna move it to up here, which we can, right? When we're dealing with a bunch of conjunctions, it doesn't matter which order we take them first. So now I'm just going to join these into a conjunction. So if and only if X belongs to A intersection B, right? And X belongs to C. And then if and only if X belongs to, now I'm going to join these into a single intersection. X belongs to A and B, intersection C. That is it for item L. Now we have to do, let's see, which one's next? Oh, it's N. So the next one that we're dealing with is right here. So maybe let me erase all of it. My pen is not working anymore. Maybe I have to reboot it. So let me try to reboot all this stuff. Okay, should work now. So the next one that we want is item to do N, right? So for N, we have that X belongs to A union. So this is going to be A union B and C, intersection C. So we're going to say if and only if. First, we're going to unravel these, right? If and only if X belongs to A, we're going to first unravel this union here, or X belongs to B intersection C. Now we're going to unravel this this intersection if and only if X belongs to A, or X belongs to B and X belongs to C. So I unraveled that intersection. And what do I want to get to? I want to get to an A or B and A or C. So what I'm going to do here is I'm going to say if and only if X belongs to A, and this says or X belongs to B and X belongs to C. So I'm going to say if and only if X belongs to A or X belongs to B. Because if X belongs to A is, if X does belong to A, then adding the or statement, it doesn't change the truth value, right? And then we're going to do here if X belongs to A or X belongs to B. And I'm just going to put parentheses around here. And then the next one is going to be and that's going to be X belongs to A or X belongs to C. And we're going to put a parenthesis here. So let's just take a moment to analyze what I did here. So this is true, this statement here is true in two cases, right? If X belongs to A or X belongs to B and X belongs to C. So in the case that X belongs to A is true, then this statement here is already true, right? We don't have to worry about it. In the case that X does not belong to A, then it means that X belongs to B, right? So if X belongs to B, then now this statement here is true because X belongs to B. And it has to belong to C, right? So if X belongs to C, then also this statement is true because of this X belongs to C. So the conclusion here is going to be if X belongs to A. Now we're going to join these. If and only if, let's join this first parenthesis, X belongs to A or B, so A or B in the union, right? And X belongs to, that's going to be A or C, so that's going to be A union C. And now we're going to join this and using a conjunction, right? So if and only if X belongs to, that's going to be A union B intersection with A union C. And that is it for item N. Okay, so for item O, we're trying to prove that A is a subset of B if and only if the union of A and B is equal to B. So because we have the if and only if, we're going to do a two-part proof, right? So for O, part 1, we're going to assume that A union B is equal to B, and then we're going to show that it leads to A is a subset of B. So we're going to say let Y belong to A, right? And we want to show that it must belong to B because we want to show that A is a subset of B. Well, if Y belongs to A, then Y belongs to A union B, because remember that A union B has all the elements that are in A and all the elements that are in B, right? So if it is in A, it's definitely in the union. However, but A union B is equal to B, right? This is what we assumed. So it must mean that Y belongs to B. So we have that Y belongs to A implies that it is in B, thus A is a subset of B. So that is it for part 1. Now for part 2, we're going to assume that A is a subset of B, and then we want to show that A union B is equal to B. Now, because this is an equality, right, we do have to show that B is a subset of A union B, and that A union B is a subset of that. So we're going to have to kind of do a two-part proof here as well. So from here, we're going to say let maybe Z belong to A union B, right? Then Z belongs to A or Z belongs to B. So we have that A is a subset of B. Now, in this line, Z belongs to A or Z belongs to B. So in the case that Z belongs to A, we have that A is a subset of B, so Z belongs to B in either case, right? In either case. So whether Z belongs to A, because A is a subset of B, so it belongs to B, or Z belongs to B, in either case, Z belongs to B, right? So what this means here, thus, A union B is a subset of B. Now we have to show the other way. We have to show that B is a subset of A union B. So we're going to say, let X belong to B, right? Well, if X belongs to B, then X belongs to B or X belongs to A. Because if it belongs to B, the statement here will always be true, right? So then X belongs to B union A, right? Actually, maybe I'm going to do this in a different order. So X belongs to A or X belongs to B. Thus, X belongs to A union B. Therefore, B is a subset of A union B, right? So we've shown here that B is a subset of that, and then we have that A union B is a subset of B, and B is a subset of A union B, so B is equal to A union B. And that is it for part O, because for part 1 we assumed this and showed that it lead to that, and then for part 2 we assumed this and showed that it leads led to that. So we have definitely proved here the biconditional. That was a lot, but we got through it. So the next one that we have to do, let's see, I believe that it is going to be item Q. Yes, let me just erase this. So for item Q, we want to show that if A is a subset of B, then A union C is a subset of B union C. So let me just finish erasing this and we'll prove that. Okay. So for P, actually Q, we're going to say let A be a subset of B, right? And we want to show that this is going to happen here. Let A be a subset of B. So we're going to say let Y belong to A union C, right? If Y belongs to A union C, we're going to begin here because we want to show that if Y is in A union C, it's also in B union C. So let Y belong to A union C, then Y belongs to A or Y belongs to C, because that's the meaning of it being in the union, right? Note that A is a subset of B, so Y belongs to B or Y belongs to C. Because if it is in A, then it means that it is in B, right? Thus, Y belongs to this B, Y belongs to B or Y belongs to C, we can join that into a union. So Y belongs to B union C. Therefore, A union C is a subset of B union C because we assumed that it was contained in A union C, and we showed that it necessarily leads to it being contained in B union C, so it is a subset. And I guess the last one that we have to do is we have to do R, which is kind of similar here. So let me just change this. We're also assuming that A is a subset of B, but then we want to show that A intersection C is a subset of B intersection C. So we're going to say let Y belongs to A intersection C. Then Y belongs to A and Y belongs to C. And then note that A is a subset of B, so Y belongs to B and Y belongs to C. Now this is true because if it belongs to A and A is a subset of B, then it means that it belongs to B, right? And this other part here wasn't changed. It just remains the same. Let me just remove these lines here. Okay, and now we're just going to join this with a conjunction. So Y, not conjunction, rather, intersection. So Y belongs to B and intersection C. Therefore, A intersection C is a subset of B intersection C because we assumed that this element was here and we showed that it must then be in this set. So that is it for problem 7.